What's up, kids? This is Mr. Carlson, C squared mathematics, and this is your last lesson of trigonometry. Can you believe it? It's the last lesson. So 7.7 dot products. That's what we're going to be going through today. We're going to go through 2 questions of the bell work, homework quiz, and then dot products. It's probably one of the easiest lessons this week at least. So let's get started. I'm excited, though I'm really sad because I really like trig, and always going through the last lesson of trigonometry is a tearjerker, to say the least. Let's go through this question. Let V be the vector from initial point P to the terminal point P2. So P1 to P2, right, in terms of I and J. So there is a formula that we're going to utilize in order to find this. So I'm going to write the formula here. It's x sub 2 minus x sub 1, and then times I. And then plus, this is y sub 2 minus y sub 1, and then j. So this is my formula when I want to find the position vector. So this right here is what we call position vector. So if you see this on your homework quiz or tests, when you're looking at position vectors, you're going to be using this formula. So what does that mean for us? Well, v equals, I'm going to take 2 and then a minus a negative 1. So that's going to be plus 1. I'm just going to do it right away right there. And then this is going to be plus, and then 4 minus 4j. Okay, what this equals is just 3i and then plus 0j, which is just 3i. Okay, remember, this is not imaginary. This is a vector notation. Sounds good? Perfect. All right, I'm eating goldfish. They're kind of stale. This is scalar multiplication. Scalar multiplication with vectors. I have to find what 8w is. I need to find what 7v is. So 8w, let's do that first. I just multiply 8 to everything in my w vector. So this is negative 8i and then minus 32j. And then my second one, I want to find 7v. So multiply 7 to my whole of my v vector. So this is negative 63i and then plus 63j. So my third step, finally, I want to do 8w plus 7v. So now I'm just going to be straight up, adding them, essentially. So negative 8 minus 63, that's going to be negative 71i, and plus negative 32 plus 63 is 31j. This is my final answer. So very short, sweet, to the point, nothing too serious, right? Right. Okay. Pause the screen if you need to. Let's get started. Homework quiz. 5 questions, 25 minutes. Review your answers if you need to. Send any partial credits to me. Dot products. Let's go to town. We're going to ask, what is a dot product? And how do I use in them and to solve problems? So we are going to use them to solve problems just like what we did yesterday with vectors, but not a lot of problems, mainly with regards to work. So I'm looking through my key. So yeah, mainly with regards to work, that's how I'm going to use dot products. So again, very physics-like, very physics indeed. We're going to get started. What is the basic foundation of dot product? In other words, what's the definition? It's this. Now notice how there's multiplication here. Well, think about it. Yesterday, we added and subtracted vectors. We technically I guess, divided vectors, but not really. We mainly just added and subtracted vectors. And now we're going to multiply vectors. And here's how you multiply vectors. Okay, it's using the dot product. So the dot product of v times w is defined as follows. I take the a's and multiply them, and then I add them to my b's. And that's it. Okay, so the sum of the horizontal components, or is the sum of the products of the horizontal components and the products of the vertical components, which is my b's, because my horizontal is my a's, my b's are my vertical. So let's go to town. Let's actually go through some examples here, okay? All right. So A, if I want to find V, that's not V, that's W. If I don't find V and W, what I take is my horizontal components, multiply them, and then I add them to my vertical components, my B's. Now notice there's no I's or J's anywhere. It's a dot product. So I'm actually multiplying these together. I'm getting something completely different. So I don't actually get a vector back out. I'm not getting I or J or anything like that out. So this is negative 15 and then minus 8, which is the same thing as negative 23. So no I's or J's anywhere in my problem. It's like a straight up number, which is really odd. Okay, if I do W times V, now notice, if I do W times V, do I get the same thing? Well, I get negative 3 times 5, and then plus, and then 4 times negative 2. In this case, yes, I do get the exact same thing. Okay, nothing changes. I get the exact same thing. Now, if I do C, what if I want to do V times, I always want to write a W here, V times itself, V. Will I get something really odd? No, not really. I just take 5 times 5 and then plus negative 2 times negative 2. So this equals 25 and then plus 4, which equals 29. Okay? So I hope this kind of helps you with it's a very simple formula. You just take the first two my horizontal components, my A's, multiply them together, add them to my vertical components B, and I get that. Pretty cool, right? In pre-calculus, if you take pre-calculus with me, we see some applications of this, and it's really sweet. Okay? So what I want to do now is go ahead and, because this is something that you'll see on Math Excel, go ahead and try these on your own. I'm going to pause the screen and I'm going to show you just all the work. But a lot of it has to do with what we did yesterday. So with basics of vectors, what we did was we knew how to add them. So you would need to do that in parentheses first, add them first, add V and W, and then find the dot product between U and that vector. Same thing here, multiply 4 to U, and then find the dot product between that answer and V. So go ahead, pause the screen, see how far we get. And then when you come back, I'll have them both up. So try to do both, and when you come back, I'll have all the work for both of them. Perfect. So this first one, U is 3i minus j. V plus W, when I add V and then W, I get 3i plus 6j. And now I want to find the dot product between those two. So 3 times 3, negative 1 times 6, and I get 9 minus 6, which is 3. Here, my 4u, when I multiply 4 times u, I get this. Now I'm technically multiplying that via dot product, with my v, my vector v, 3i plus j. Now the reason why I put this in kind of quotations is because you're not really doing this. You're not like foiling it out. Like most of you will probably think, oh, I'm going to foil that out. Ha, ha, ha. No. So it's not exactly like this. I would never, ever, ever write it like this. I'm just writing it like that for the sake of time. That this is now my 4u. This is my v. I want to find the dot product between them. So 8 and 3 multiplied together, negative 4 times 1 multiplied together. 24 minus 4 is 20. Okay? Sweet. If you got that, you're amazing. If you didn't get that, then you're still amazing. Keep trying. So, formula for angle between two vectors. So this is the formula between angle of two vectors. So cosine of theta equals vector v times w, just any two vectors, doesn't matter, all over my magnitude my magnitude of those two angles. So my magnitude of that angle and that angle multiplied together. If I wanted to find the actual angle measure of that, I just take the inverse. So if I did an alternative dot product formula, you receive this formula. So there is an alternative dot product formula. I didn't show that to you, so just for the sake of time, but if you're interested in that, just look it up. What's the alternative dot product formula? And if you solve for cosine, you actually do get your angle between two vectors. It's actually really interesting. So we're going to go through at least one example of that, and then go through what's called orthogonal or perpendicular vectors, and then a couple of application questions. All right, make sure you pause the screen. This is the primary one I'm going to use. I'm going to primarily use the inverse because that's just the easiest. They literally equal the exact same thing. But to skip a step, I mean, just do the inverse, right? So find the angle theta between vectors v and w, shown in this. So shown in this figure right here. Now this is what the angle measure means. Now yesterday what we did was we found the resultant. So the resultant would look something like that. It looks kind of like a parallelogram. It doesn't look exactly like a parallelogram because that's clearly not the resultant. I did it completely wrong. I don't know what the resultant, like what the parallelogram would look like, but it will look something like that. That would be like the resultant angle or the resultant force. That's sort of what we did yesterday. And then what you can do is find the angle measure of that resultant force by going like this. So you can find that angle measure, and that's the directional angle of the resultant force. We actually did that in our last example of the previous video, okay? That's why we use cosine all over sine, or cosine equals your adjacent all over hypotenuse, because you're adjacent here and then your hypotenuse. That's definitely one way to do it, but this is a resultant. I don't really want the resultant here. What I want is just a straight up angle between the vectors. So as you can see in the picture, this whole angle here. Now I could, and I already know that this is 90 degrees. So this whole thing is 90 degrees. I just need to find that little guy and then that little guy. How do I find that? Well, you use the following formula. Before I use the following formula, I need to find my magnitudes. So what is my magnitude of V? The magnitude of V is taking 3 squared and then -2 squared. So that's just 9 plus 4. So this is radical 13. And then I also need to take for my second step the magnitude of W. So I need to find the magnitude of both is essentially what I'm doing. Okay. And how do I do that? Take -1 squared and then 4 squared. So 1 plus 4 squared, which is 16. So this is radical 17. So really, again, guys, just as a reminder, a magnitude essentially means distance or length. So what you just found is this length. That's really just what you found. You found the length from the origin. All right? That's literally what you have found, the length from the origin. Okay? So now that you found that, you have both lengths. Let's use our formula. Theta equals the inverse of cosine. And I'm going to take vector v times vector w, which is my dot product. The top is my dot product, as you can see. And then all over magnitude of v times the magnitude of w. Okay, this is my formula that I'm going to use from my last slide. Let's go to town. What's the dot product of v and w? Well, I take 3 times -1, so 3 times -1 plus -2 times 4. So that's the dot product, all over just radical 13 and then times radical 17. Okay, this all equals -11. When I simplify the numerator, I just get -11. And this equals, oh, I should probably put my, man, I'm just so awful. Oh, shoot. Oh, geez. You see that? I should be putting this in parentheses here. I'm so not awesome. Should be putting that in parentheses. Even right here, I should have an inverse of cosine. I apologize. But this is negative 11 and then radical 221. And then when I find the inverse of that, so that's also the inverse of cosine, just letting you know. When I find the inverse of that, this is 221. 221. This equals 137.7 degrees. So this whole angle measure right here is 137.7 degrees. Okay. Not too terrible, right? Just, again, plug and chug. You're trying to find the angle between two of these vectors. You first have to find the magnitudes, then you find the dot product in the formula, you put it all together, cha-ching. Right? Sweet. Let's erase this. We're almost done. Can't you believe it? Oh my gosh. So orthogonal, or what we call perpendicular. So when I say orthogonal, it just means perpendicular. It's just a fancy word for perpendicular. So two non-zero vectors, v and w, are orthogonal or perpendicular if and only if the dot product is equal to 0. So, and why is that? Why does that work? Because 0 and then the dot times v is still 0. So 0 times your vector, if 0 is a scalar of your vector, then that's just equals 0. So the 0 vector is orthogonal to every other vector v. So this is what it would look like. This is just a 90 degrees perpendicular angle. And where cosine is also cosine of theta equals 0 at 9, and sine of 0 equals 1, or sine of 90 degrees equals 1. That's not something you really need to know. But all you need to know is how can you check to see whether or not it's orthogonal. So you'll have a couple questions on your homework that'll essentially be like, yo, can you check to see if it's orthogonal? Well, clearly, I'm giving you the picture, yes. Okay, they are orthogonal, but obviously you won't always have a picture here with you. So you'll just be given this, and you'll have to figure out how and why, or basically how they can be orthogonal, or if they are orthogonal. How do you do that? You just find the dot product, guys. So this is just 6 times 1, because that's my eyes, and then plus negative 3 times 2. So this becomes 6 minus 6, which of course is 0. So that means, yes, they are perpendicular, or what we call orthogonal, okay? And obviously you can see in the picture it's orthogonal, okay? So you can see in this picture they're definitely orthogonal. That's it. Simple as that. So let's go through 3 more questions, 3 more slides, and I have one slide of definitions of applications for dot products. The primary application for dot product is work. So vectors usually have to deal with force, as we saw yesterday, and then dot products have to deal with work. So we're going to go through that, and then the last 2 slides are just examples. All right? But that's orthogonal vectors. You can see whether or not it's an orthogonal vector by just completing the dot product, and if it's equal to 0, then it's orthogonal. So what is my work formula? Well, my work formula is as follows. It's W equals F times vector A to B. So if it's moving from A to B. So what does this actually mean? I'm going to show you what it means. And I'm going to actually give you a better formula than this. This formula is kind of janky. I want an easier formula to work with. Ready? So work literally just equals the magnitude of force. That's your F. So the magnitude of force. We already know how to find that. It's literally just this. Okay? That's literally the magnitude of force. It doesn't write it like that. So it's kind of unfortunate, but it should. It's the magnitude of force. And then the distance from A to B. The distance from A to B. Another way to rewrite this is when the force is being directed on the object is at an angle. So when the force being directed on the object is at an angle, which it always is, okay, we can use the alternative work formula as follows. Okay, this little work formula right here. Right, so I can take F, my magnitude of force, times my distance, and I can change that to be F, my magnitude of the force, right here. My B is the distance, that doesn't change, the distance over which the constant force is applied. And then right here, I'm going to move my little face so you can see it. Wow. So the theta is the angle between the force and the direction of the motion. So this theta is the angle between the force and direction of the motion.